Good afternoon, everybody. Hi, I'm Harshitha Menon. As Pritish introduced, I'm a new PhD student. I work with Professor Kale in the PPL group. Today, I'll be presenting our work on epidemic algorithm for distributed load balancing. So this is the outline of the talk. I will start off with motivating the problem and few challenges that are faced in load balancing, few strategies that are being used today, and then go into the details of the distributed load balancing algorithm that we are proposing, and show some of the evaluations in comparison to other existing load balancing strategies, and conclude. So in parallel application run, even a slight imbalance can cause resource wastage and reduce in performance of the processes. So load imbalance is a critical factor that can cause the application scaling to perform badly. So as we move towards the exascale era, given the millions of processors that we're going to get, the chance that even one processor becomes overloaded in comparison to the average load of the system is quite high. So it becomes all the more critical to focus on load balancing problems. So for some applications, the load of the application, load of the processor doesn't change or vary over time. So for them, we can use static load balancing strategies. So statically distribute the task and get done with it. But for many applications that we deal with today, the computational load varies over time, and it is quite hard to predict. So this requires a load balancing strategies that adapts over time dynamically and then does the right load balancing strategy. So some of such applications are like weather simulation code or AMR, molecular dynamic simulations, where the load varies over time and it's quite hard to predict. So the load balancing algorithm we are proposing has been studied on iterative applications with persistence. And so in our context, the application is composed of large number of migratable units. And the load balancing strategy is periodically invoked. In Charm++, the load balancing framework is based on the principle of persistence, which states that if we decompose the computation into migratable objects, the computation load and the communication pattern tends to be persistent. So past is a good predictor of the future. So we use that principle of persistence and do the load balancing. So the Charm runtime system instruments the application task for us at a very fine-grained level. So now we have the load characteristics and the communication pattern between the tasks. So when the load balancing strategy is invoked, it gathers the statistics of load communication pattern at a certain specific location. It could be a centralized location in the case of centralized strategy, or could be distributed. And then it executes a load balancing decision and decides to migrate the task based on the new mapping. So this is the required background for this particular thing. As we know, load balancing has been studied extensively in literature, and many strategies have been proposed. So I mention a few of them here. So many applications use centralized strategy, which collects the load information and does the decision, carries out the decision at a central location. So the advantage it has is that it has a global view of the system, and it can do a better load balancing decision because it has a full view of the system. But as we know, it presents a clear bottleneck beyond a few thousand processors. So alternatives to the centralized strategies are the distributed strategies, which are very scalable, but it uses only the neighborhood information to make to perform autonomous decision. So because it has a limited view of the system, only its immediate neighborhood, it doesn't usually yield good load balance. So examples of this distributed strategies are the diffusion-based strategies. So to overcome the disadvantages of centralized and distributed, hierarchical strategies have been used, and it's been used in LeanMD to scale LeanMD to 300,000 cores. So this is a good mix of centralized and distributed strategy. In this case, the processes are divided into subgroups, and each root on a subgroup is in charge of taking the decision for that subgroup. But it's kept in a hierarchical fashion. So once the decision has been done for the subgroup, an aggregate information is passed on to the higher levels of the hierarchy. So this is quite scalable and usually yields good quality, but sometimes it suffers due to excessive data collection at the lowest level, and if the levels of the hierarchy is quite high, then the quality is not that good. So here we see that on one hand we have the centralized strategy, which has a global view of the system and hence can make good decision, but has performance bottlenecks. And on the other hand is the distributed strategy, which is very scalable, but has only a very limited view of the system, because of which the load quality of the load balancer suffers. So we propose a load balancing strategy, which is designed to overcome this drawback of both centralized and distributed. So this is a fully distributed strategy, and we use partial information about the global state of the system to do the load transfer. So this system is scalable because it is fully distributed, and yields good quality because of the fact that we use a partial information of the global state. So our load balancing strategy can be conceptually thought of as two phases. First phase is the construction of local representation of the global state of the system at each processor. So this spread of information is done in the same fashion as gossip spreads through Grapevine, which is one of the reasons our load balancing strategy is named Grapevine. After the information propagation stage, the distribution of load happens based on the local representation we have. So first we talk about the information propagation stage. So the information here is the information about the underloaded processes of in the system, and this information is spread to the overloaded processes. For this propagation, we use a protocol which is inspired by epidemic algorithm, or also known as gossip protocol. So gossip-based protocols have been extensively used in distributed systems for information propagation, failure detection, garbage collection, and multiple other things. So we use a flavor of gossip protocol for our load balancing strategy. So the goal here is to spread the information about the underloaded processes to the overloaded processes. So an underloaded processor starts the infection or gossip by sending its information to randomly set of processes. So the random subset of processes is called the fan out. So once a processor receives the information, it combines the information that it already has. So this is its knowledge base, updates the information, and sends it to a new set of processes. And this propagation goes on. One key thing to note here is that there is no explicit synchronization. We don't want any barriers. So the way it is implemented is, underloaded process starts the gossip. On receiving a message, it updates the knowledge base and randomly samples a set of processes and sends the information. So there is no synchronization, there is no barrier. But we need to terminate this. So the termination is based on TTL, time to low. Every message is assigned a TTL. And any time that message is received and forwarded, its TTL is decremented. So it will be forwarded only till a certain number of times, certain number of hops, beyond which it won't be discarded, it won't be forwarded at all. So, but for the purpose of analysis, we assume that the processor, let's assume that the processor communicates in synchronous round. So as you saw, this is a lightweight information propagation scheme, and the number of rounds required for the information to be propagated to all the processes in the system with high probability is O of log n to the base f, where n is the number of processes in the system and f is the fan out. So this figure illustrates the dependence of number of rounds required to propagate the information on the system size. As we can see, as the system size increases, the number of rounds required increases logarithmically. And if we increase the number of fan out, the number of rounds decreases. So we have two schemes, two flavors for information propagation. One is a naive scheme where a receiving processor updates its knowledge base and randomly selects uniformly at random F processors to send the message to. So this selection may include other underloaded processor. But the other scheme, which is the informed scheme, is very similar to the naive scheme, except that the selection of peers incorporates the current knowledge. The current knowledge is the set of underloaded processors we already have. So the selection process is biased not to include them while forwarding the message. This is improvement on the naive scheme and helps reduce the number of rounds required to propagate the information on information. This particular graph here shows a system size where 50% of the processors are overloaded. So the informed scheme takes lesser number of rounds in comparison to the naive scheme. So till now, in the information propagation stage, we have a partial list of underloaded processors in the system. So the overloaded processors now decide in isolation to transfer the load. So this transfer of load is totally decentralized, and every processor makes its decision in isolation. So there are two schemes again for this. One is a very intuitive scheme, very simple scheme, in which you select the processors uniformly at random from the list you have. And the other one is the informed scheme, in which we randomly select the processors based on the probability. And the probability is assigned inversely proportional to the load. So basically, if a processor is more loaded than the other one, it has lesser probability of getting picked. That's as simple as that. So the informed transfer is done like this, where Pi is the probability assigned to the ith processor, Li is its load, L average is the average load of the system, and Z is the normalization constant. So as we see, this is not limited to just the load. It can be extended to other cost models to include the load or a weighted sum of load and topology, or load and memory, or there are various flavors that we can come up with. But these are the two simple schemes we have compared with currently. So here is a proper comparison of the naive and the informed scheme. The first column is the initial load of the underloaded processors. The second is the probabilities assigned. In the naive scheme, all the processors are selected uniformly at random, so they have the same probability. The third column is the work units transferred. And the fourth column is the final load of the underloaded processors after the load balancing stage has been done. So as you can see, in the naive scheme, since the work units are transferred irrespective of the initial load, some of the underloaded processors tend to become overloaded. And the maximum load in that case becomes 44, where the average is about 35. But in the informed transfer, the work units are transferred based on the probability distribution, hence leads to a better load balancing. And the maximum load we get then is about 38 in comparison to 35, which is the average. So the informed transfer is quite efficient in that manner. So now one question that we can ask is, in the information propagation stage, what if the overloaded processors don't have the entire information about the underloaded process? What happens then? What if we decide to terminate what if we decide to keep a small TTL? So here is a comparison of that, which shows where the overloaded process have only partial information of the system. This is the 8K processors. All 50% of them are underloaded and 50% overloaded. So on the x-axis is the number of processors the overloaded processors are aware of. So on the left-hand side, this means that overloaded processors are aware of one random underloaded processor. And on the right-hand side indicates overloaded processor is aware of all the underloaded processors in the system. So as we know, the performance is determined by the most overloaded processor in the system. So the metric that we use is I imbalance, is the ratio of max versus average. So this graph plots the max load and the imbalance ratio along with the standard deviation. So here we see that if we have about 10 to 54 information about 10 to 54 underloaded processors, it helps in bringing down the imbalance quite a lot, but maybe not the optimal one. But we also see on the other hand that the entire information is not required to do a good load balancing. So that gives us an opportunity to select suitable parameters where we can trade off between quality or overhead and various other things. So it's very tunable in that regard. So one key thing I again want to reiterate is that the entire information is not required to do a good load balancing. Partial information is sufficient. So now I go on to present the comparison of this algorithm with other load balancing strategies. Here we make a run of two applications, LeanMD and AMR. LeanMD is the molecular dynamic simulation written in SHARM, which simulates the behavior of atoms based on Lennard-Jones potential. AMR is a new benchmark that has been written in SHARM. So it starts off with computation being a coarse structured grid of uniform size, and then the refining and coarsening goes on, which leads to quite a lot of imbalance in the application, and thus requires frequent load balancing. So these applications were run on BGQ Vesta, and we compare with 3 on the left-hand side is the centralized strategy, diffusion-based load balancing strategy, and hierarchical strategy. And the metrics we evaluate are time per step, excluding the load balancing time. So that gives an indication of the quality of the load balancer. The overhead incurred by the load balancing strategy, which includes the cost of collecting the statistics, doing the decision, and also migration of the objects, and the total application time, which is the real indication of whether this load balancing strategy was useful at all. So first we start off with the LeanMD. We scale it to 32K processes. Here is the time per step evaluation of that. One key thing I would like to notice is that the Grapevine load balancing strategy performs very similar in quality with respect to the centralized strategies. This is the time per step. The next one is the overhead incurred for all the load balancing strategies. As we can expect, the centralized strategies have a high overhead because of the stats collection and the decision making. And some of the strategy, like the greedy LB, is not a refinement-based strategy, which leads to a lot of migration. So centralized strategies tend to have a high overhead, but the distributed schemes have low overhead in comparison to them. The hybrid strategies, because they are the processes are divided into subgroups of 512 cores. As we increase the number of processes, the time for the load balancing overhead also decreases. So now we go on to the total evaluation of LeanMD. So after taking into consideration the time per step and the load balancing overhead, we find that the centralized strategies, the overhead exceeds the benefit in this particular example. So therefore, if we do them very frequently, the overhead overshoots the benefit and leads to a reduce in performance after using the centralized strategies. Whereas the hybrid strategy gives us performance benefit and also the diffusion-based strategy to a certain extent. But the Grapevine gives the best performance in terms of total application time. This is achieved due to the quality as well as less overhead in comparison to the other strategies. Now we go on to the evaluation of AMR. AMR required very frequent load balancing steps. So we look at the quality of the load balancing strategies based on the time per step. So again, the quality is equivalent to the centralized strategy that we have used, which is AMR LB or diffusion-based LB, which is the AMR LB or the refine LB. And diffusion-based LB does not tend to give good results because it has only a very limited view of the system, and it is generally used only to improve the load balance rather than to achieve a global balance. So the quality is at par with the centralized strategies. And now when we look at the overhead incurred, the overhead of the distributed schemes are quite low because they are distributed in nature. And the centralized strategies tend to have a lot of overhead. So this is again in similar regards to the LeanMD results that I've shown. So again, the total application time, the load balancing overhead really exceeds the benefit of the most of the strategies. So, and since we are using this load balancing strategies very often, this leads to the overhead exceeding the benefit and leads to a performance degradation while using most of the load balancing strategies. So diffusion-based load balancer gives marginal benefit, but then the Grapevine gives the best performance in these regards, primarily again due to the quality as well as less overhead. So in conclusion, we have proposed a simple strategy which can be, which is a fully distributed strategy, and using a partial information about the global state of the system. It's very tunable. You can optimize either for cost or quality, and there are various parameters you can tune and play with to optimize for specific application-specific requirements. It also scales well, primarily because it's a fully distributed strategy. And yeah, that's all I have. Thank you.
Let's pick a number 32K processor.
How many rounds were needed for the particular data point, say LeanMD data point or AMR data point for 32K?
Rounds, hops. I used 0.5 times logarithmic of number. So
0.5 log n to the base 2?
Yeah, log n to the base 2
okay.
Fan out.
So I guess, okay, let me calculate that then. 5, 15, so it's like 7 or 8 for 32K processors? No. Yeah, 7 or 8, yeah. Okay. Good. And did you truncate what information you sent to the other people?
No, this was not required. Oh, I forgot. The information is primarily the processor number and the load of the information. This is very small, so it was not required to truncate. You could send the whole information that you have.
Okay.
But that's an addition that we can use. If we find that the information that's being sent is a lot, we can use only partial, randomly sampled partial information to propagate it.
And you describe how, once you have the rounds done, how you decide who to send work to?
Yes. So based on load of the system. This is the probabilistic transfer. The informed strategy is so you randomly sample from the list of underloaded processes you have based on the probability, and probability is, in this case, is inverse proportional to the load, based on the load.
We have time for a couple more questions. Anyone ask them? And I'll ask one then. It seems to me you have a good way of getting the load information across a large system without doing a centralized collection. What about stuff like communication information? Can that also be incorporated into this? framework?
To a certain extent, because usually it can definitely be done. It can definitely be done. Depends how much of an overhead do we want to incur by sending the whole communication information across. So for example, in Changa we have n-square communication matrix, so it might not be really feasible to send the entire communication matrix across wherever it's required. But a partial information could definitely be sent if needed.
Do you take into account network topology when deciding about load balance?
No, currently we
Repeat
only...
the question, please.
Yeah, so do we consider topology while taking the load transfer into account? Currently the scheme doesn't take into account topology, but as I mentioned, this metric can be modified to take a weighted sum of the load as well as the topology. So, number of hops between the underload process and mean, depending on that, the transfer could be made in that regard. Or the other, it's quite configurable, so you could decide to send the information propagation stage to your nearest neighbor. And
What would be the core function for that? Not just the number of hops, but doing the work remotely may be more expensive than it's not necessarily just the number of hops. It may be depending on shape of the network or the topology itself, not just on the distance. So the function would take into account network topology could be very complex. In fact, not that simple as this one.
I guess the question is, if you're not collecting all of the information about the global state of the program, what is the right information to send? So let's say you want to take into account topology effects. Mm-hmm. What is this person going to gossip to someone about?
So as I'm thinking, I might be wrong, you could send just the information that it is underloaded and what the load is. When the sender is deciding who to send to, it could, in an ideal world, decide to transfer the load to the person who is nearest in their topology. So that information is distributed. When we know the rank of a processor, we know how far they are. So this is what I'm imagining, but I'm pretty sure there are much smarter ways of doing these kind of things.
But also Harshitha herself is working on or has worked on the Scotch group on graph partitioning, distributed graph partitioning, and that when communication is that important, you'll do something like that.
This is primarily for computation load, where computation load is the bottleneck and is the one that's causing load imbalance. We have another work which decides which strategy to use based on the application characteristics. If we find that this is not a computation-intensive benchmark and it's a communication bound, we have strategies like Scotch, Metis, or other strategies which we can use to decide.
Let's thank Harshitha.
Thank you.